Hey, this is Matt X with Sitavism Sana. Today we're discussing how we working on projectile and freefall. So exactly, a projectile is an object that moves freely under influence of gravity only. So if nothing acts on an object, like whenever you are standing wherever you're standing and you decide to throw something up and it comes down, it is projectile motion because the only force that it acting on the scenario that I just drawed is force of gravity. So in simple terms, when we're talking about projectiles where there should be no friction at all or no other force acting on it, and gravity should be the only force acting on it, and it should be accelerating at a normal or the most famous 9,8. Okay, now let's analyze the projectile motion. Okay, let's assume this is the part that a ball that you're drawing here. We assume there is a ball. Uh, this is a part that is like you're drawing a ball and catching it. So it start from this point, that is a point of launch, then it goes back down like a more of like a parabola. Okay, this time that we're analyzing, this is of same height, and let's the highest point here is the turning point. Here we have of same height. Okay, whenever we're throwing a ball upward, it's going to take the very same time for it to come down. And when you're throwing a ball upward, as I've said earlier, that the only force acting here is force of gravity. This is G himself is putting everything down in an acceleration of 9,8 meters per second square since its acceleration. So if here it's a velocity where you launch, I call this point of launch, where you're launching the ball. In the point of launch that we have initial velocity. The initial velocity of this case as the velocity that it was launched. Then I can call any number. Let's say I decide to call it 3 meters per second. And the time that the ball then it goes up but for some time, let me call that time t, it goes up till it's reached turning point. About turning point, that where the velocity reaches zero. So in simple English, the ball stops before it changes direction. Here now, the 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 direction of the velocity stopped. So if this was positive 3, at the very same height, we're going to reach the very same velocity. Velocity here is going to equal to negative 3. Negative 3 is the very same as this one, same magnitude but different direction, because here the ball is moving up this direction and here now it's moving down. The other thing to note is that the very same time for the ball it took uh, to move this way up is the very same time that we're going to take for it to reach the very same height. So the very same time that the ball is going to take for you to throw it up, to go up till the turning point is going to be the very same time that it's going to come back. That's simple English. Let's keep on evaluating the boy throwing the stone up and catching it through our different uh, graph of projectile motions. The first one that we're going to evaluate is going to be position versus time. Position versus time is one of the simplest presentation of projectile motion, because in this case we simply say you draw exactly what is on the scenario. Simple as that. So if the ball went from a position that it was launched and went up and returning point and come back, that's what you draw. Simple. But then I did say that at the time that it took to go up, the very same time that it will take to go down. So I call this one time 1, time 2. So moving from this time to here is equal to moving from this time to here. And the next to evaluate is velocity versus time. Velocity versus time is like looking at the speed on this case. Okay, what is happening on the speed? Because it was launched, or it means it was shoot up, like the guy drove it up, or maybe it was in a hot air balloon that we're going to discuss later. It had initial velocity, so now the ball have initial velocity that it was launched with. But because I said gravity is always pulling everything down with the acceleration of 9,8, it means it's going to deaccelerate as it's moving up. It will deaccelerate as moving up till it's reach a time I call time 2. Time 2, where it is 0. So I call that time here time 2. So it's going to deaccelerate at constant acceleration of 9,8 till it reach 0 at time 2. Okay, because I said the time is going to take for it to come here, from here to the very same height of launch is the same, and the velocity at launch time, I call it velocity initial, is going to be equal to velocity. Here I did explain that. So this is v2 and v3. So it's going to proceed till it's reached that height. This is the height. This is the height. So at v3 here is the very same height that it was launched. Now it have very same velocity, but at a negative, or should I not say negative, but opposite direction. And lastly, we're going to evaluate acceleration versus time. As I've been elaborating or maybe emphasizing this, the acceleration for projectile problems is always 9,8. 9,8, I keep on repeating, meters per second squared. Note the unit here that you need to mark. Okay, whenever you have to represent this on a graph, you just have to write 9,8 and you draw a straight line, because this 9,8 is not changing acceleration. On the past example, we've been having initial velocity as like we've been drawing, and I talk about the case of being on a moving object like a hot air balloon. Now, what will happen if you are dropping the object? Simple as it sounds, you're dropping the object, meaning the object is released with an initial velocity of 0. So you started the motion with 0 velocity since it was dropped. Now force it to act on it to pimp it up. So it just dropped. Simple. If we were to represent that on a position versus time graph, as I've been saying, in position versus time graph, you just draw exactly the scenario. So the ball head was in a certain height up, and then it was dropped. Simple. It was dropped like that. So just draw exactly what is in the case as it was been dropped here. Remember that because it was dropped, it didn't go shoot up till it's at the turning point, then come back. It just went down. Going forward, we're going to evaluate change in velocity versus time of a dropped ball, or a ball with an initial velocity of 0. So just dropping it down. So the initial velocity, as we're going about, changing velocity versus time. Initial velocity is obviously going to be 0, where it's that at the origin of the Cartesian plane, and then it's going to be pushed by gravity as it moves down. It's going to be pushed by gravity of 9,8. So it's going to be pushed by gravity of 9,8. Simple for a drop ball. For change in acceleration versus time, it's always been the same. The acceleration doesn't change here, meaning it's going to just go straight as time goes by. It's time here, change in time here, and here we're going to have 9,8. Simple. The acceleration for whatever case when we're talking about projectile, as I said earlier in a definition, it is the only force that is acting, and this is the acceleration of an object. Simple, it can't be altered unless it hits the surface and there will be just a slight alteration. Now let's head to our next case that I've been mentioning lately, as that What if now the ball is dropped and then it crashes on another surface, then goes up and land on another surface? Okay. Now the thing. Let's evaluate this through the motion graphs again. Position versus time. Here, which I said lately, you just draw exactly what is in the case. So I'm just going to draw this. This is position versus time. But what about the most interesting, velocity? What is happening on the velocity here? First of all, I did mention that the ball is dropped. So obviously the initial is going to be 0, initiate from here. Then it's going to move further, accelerating downward till it crashes here. Here. It's going to crash here, crashes here, and the crash is indicated on the graph by a dotted line. It crashes. After crashing, something interesting happened again. It moves up again. So there is a change in direction here. We're moving down. Now we're moving up. So now we are from this quadrant to the upper quadrant. Then from that we have now initial velocity because now we're moving up. So we have initial velocity. Then from that initial velocity we trained our speed till we reach 0 at this point. So now we reach 0, we go till we reach 0 at this point. What if I number things? I number things like this. I number this 1, 2, 3, 4. The crash is at 2. The crash, the turning point is at 3. The 1 is the initiation. It's the same applies with the rest of the graph that I was explaining. So after reaching the turning point, it didn't stop exactly. It went down even further. So the velocity went down even further till it reached some height. If the ball keep on bouncing, bow, 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 bow. So same applies with the graph. The graph is going to be zigzagging like like that till it reaches 0. So the graph is going to be simple like this, more like a wave. Since the velocity is the ball is losing energy till it reaches 0. So the ball is like bang 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 bang. Exactly. And there is there is the most famous hot air balloon that examiners love the most. And it tend to, this is the bonus part of the video. This tend to challenge most of the students. What is the initial velocity of you're just dropping the ball? This can be tracked in many ways. Okay, first of all, it could be that the guy from the hot air balloon is dropping a ball, down, and they ask you about initial velocity. This is what you should know. Initial velocity of a hot air balloon is equal to the velocity of an hot oh sorry of a hot air balloon. Simple. If you're dropping the ball in a hot air balloon, it's like you're throwing the ball, because you yourself and the hot air balloon have the initial, you already have the velocity moving in. So if you're dropping it, it's like it's take the velocity of you. If you are in zero velocity, then it's going to have an initial velocity of 0. But if you're in hot air, and it has to be stated that the hot air is moving, then if the hot air is moving, then the initial velocity of the hot air balloon is going to be, it's going to initial velocity of the ball that you'll be evaluating in the case. There could be another problem. They could make it tricky another way. They could try something else. They could try saying that the person in the hot air balloon throws the ball. So now, if a person throws the ball while he's in a hot air balloon, the velocity of the ball is going to be equal to a hot velocity of launch, or should I say, yeah, launch, plus velocity of a hot air balloon. So simple. So if you're throwing a ball while you're in a moving hot air balloon, the velocity is going to add up or subtract, depending to the what to the direction of the both velocities. It's not always the hot air balloon, but it's the famous example. They could make it a helicopter or anything like that. But whenever you see something moving, then you're going to take that velocity as initial velocity, and if you're dropping it. But if you're throwing it, the velocity is going to add up, because now the ball or any object that you're dropping, could be an apple or anything, is going to add or take both of those velocities.